So this is a demonstration of what the electrical power lab is going to look like. When you arrive, you'll find that the breadboard is going to have two incandescent bulbs, the blue stripe bulbs. There'll be 3 red LEDs in series, there'll be 2 blue LEDs in series, 3 yellow LEDs in series, and 3 green LEDs in series. There'll also be a DC motor, and there'll be an analog ammeter that you can use to measure the currents flowing through the circuit. I've previously already set the voltage source to be 6 volts, plus or minus a few hundredths is fine. And then this multimeter is showing what the voltage is from the top of the board to the bottom of the board. Now you'll also need 7 patch cables. So I've got 7 patch cables down here. And your first task is really just to connect each of these items to the power supply. And so as we connect the items to the power supply, we'll begin to see them turn on. And what we're really trying to do here is we're trying to see a variety of different types of loads. They're each going to have a lot of electrical power flowing toward them. And what we can see is that as we're attaching these, more and more electrical power is being drawn. Here you can see there's all 3 of those red LEDs are being lit. 2 blue LEDs are being lit. And then over here are the yellow LEDs. And then the green LEDs. Notice that the series connections between the LEDs are already made and the connections to ground are already made. Now you might say, why don't we need current limiting resistors? We've always used current limiting resistors before, but what we're seeing is that because these are 3 of them in series, and since they need each about 2 volts, the total of 6 volts is going to be appropriate to drive 3 of them in series. Turns out that the blue LEDs are special. They have a turn-on voltage of about 3 volts, so just 2 of them is appropriate to turn on when we have 6 volts. And then the last thing that we're going to attach to the power is this DC motor that you have used in a previous lab. And you can see that when we turn that on, it begins to turn. And what I need to do now is I need to adjust the voltage so that the voltmeter still reads right at 6 volts, plus or minus a few hundredths. You probably can see or hear that this motor is turning. If I were to push it onto the bottom here, you could see it and hear it even better. So what you want to do now is you want to calculate what is the total amount of power that's being delivered by the voltage source. If you look at the voltmeter, you'll see that it will tell you both the voltage and the current. Now the voltage may not agree perfectly with this voltage. If that's the case, as for example, mine right now is showing 6.17 volts. I'll sort of show you that right here. I'm getting 6.17 volts and 0.57 amps. If you find that they don't agree with each other, my advice would be to use this one, because I think that this voltmeter is more accurate. More accurate. I have, before the video started, double-checked that the ammeter is actually pretty accurate on those voltage sources. So the 0.57 amps seems like it's actually pretty accurate. So you can take the voltage from the voltage source and the current from the voltage source and multiply them together. So I would take the 6.00 volts, I would multiply it by the 0.57 amps, and that would tell me how much power is being delivered to the circuit by the voltage source. The question then becomes how much current or how much power is being consumed by each of these elements. Well, in order to test that, we're going to take each of these jumpers out one at a time. Now, I want to warn you, first of all, these 2 incandescent bulbs down here get a little warm. They're not going to be hot enough to probably burn you, but just don't go touching them. I can touch them. I'm the professor, but I don't want you to get hurt. Also, don't rub this up against your finger really hard. That's a bad decision that I'm doing right there, because you could potentially hurt yourself. And again, someday when you're not in my lab, you can do whatever you want. But while we're in lab together, let's not do that. So I'm going to pull this wire out, and instead in its place I'm going to put this ammeter. Now the ammeter is going to have 2 leads, and what you need to do is figure out which lead is the positive lead and which lead is the negative lead. And the colors could vary, so you really can't count on the colors. What I'll say is that when we connect this, if you see that the ammeter needle has moved, then you've got it in the correct orientation. If these were backwards, I'll go ahead and show them to you backwards. If I had these in backwards, then what's going to happen is that no current is going to be indicated on the ammeter. So you don't want to put them in backwards, you want to put them in the proper orientation, and then you'll be able to measure the current. Now I've accidentally unplugged this cable, so I'll plug it back in. Now what we can see is that this, the first incandescent bulb is drawing maybe about 195 milliamps. If we were to bring this up really close, you can see that it's not quite precisely 200, so I might call that 195 milliamps. Now what I'm going to do is I'm going to go down the chain, and so each one I'm going to replace the wire that I had in there, and I'm going to go down the line, and for each one of these I'm going to measure how much current it is drawing. And so here I'm going to plug this one in. I'm going to measure how much current it's drawing. That one is pretty close to 200 milliamps, so I might just call that one 200. I'll take that one out. I'll put this one back in. Don't worry, I'm not going to do all of these, but I do want to do one more because it's interesting to see that although those were 200 milliamps, if I push this one in, and when I light this one up, the interesting thing is, notice how much current is flowing there. We're talking at maybe 25 milliamps. So 25 milliamps is not very much current. And if I take this one back out again, and I put this one in, let's skip a couple and go down to the green LEDs. So if I plug this one back in, and I go down to the green LEDs, I'm going to pull this wire out. I'm going to push this in place here. And with the green LEDs, notice that we're looking at maybe, my best guess would be about 15 milliamps is probably what that one is reading right there. And then finally we're going to have to actually move the connection for the DC motor so that it's down here. And then I will put the ammeter in series. Remember, ammeters always go in series, voltmeters always go in parallel. And when I put this in the correct orientation, I find out how much current that motor is using. It's using about 100 milliamps. Now here's an interesting thing, and this is kind of just an aside. There's a couple of asides here. First of all, motors are interesting. You remember that when we did a previous lab involving the same motor, I mentioned to you that if we try to abruptly start it or abruptly stop it, there's going to be a big pulse. And that pulse can be problematic if there are electronic elements that are in the way. What I want you to do is watch this ammeter, and one of the reasons why we're using an analog ammeter, so you can see the needle as it jumps. So here I'm going to unplug it. So the DC motor got unplugged. Now what you should observe is that this needle is going to go all the way to the right. It's going to slam over really hard, fully clockwise, and then it's going to go back to 100. So boom, just like that. So if I turn this thing on, what you'll see is that there's a huge inrush of current. Now what you can't see is that when I unplug it, there's also an outrush of current. You can't see that because as soon as I've unplugged it, then the ammeter is no longer connected. But you can see this is that inductive load that I was talking about, that you'll see this big burst of current that comes through. Now the other thing to know about this motor is that it draws 100 milliamps or so. I mean, it varies a little bit. You just have to sort of choose what you think is the best reading. That amount of current is going to vary with the load. You know, like if you're using a drill, for example, to drill into a wall, you'll notice that you'll hear the motor is going to change speeds. And as I apply my finger to this motor, I'm going to increase the load. And as I'm increasing the load, I'm increasing the power consumption, which you can see as the current is going up. And so I can actually adjust the current to be almost any value that I want it to be, just depending on how much pressure I put onto it with my finger. Now again, I've shown that in the video here because I don't want you to do this. Don't do this in the lab, but you can watch this video as many times as you want. It's totally safe. Because this is kind of hurting a little bit, but I will suffer for your learning. So what I want you to do then is, once you know how much voltage, it'll always be the same voltage because all of these elements are in parallel with one another. Once you know the voltage and you've calculated or measured the current for each one of these elements, then multiply those together to find out the power. Add up all the power that's being used by all of these elements and see if that's approximately equal to the power that's being delivered by the voltage source.